In this video, we're going to talk a bit more about how a titration works. If you have not already watched the How Much Is There video, you should do that before watching this video. So a titration setup looks like this picture here. We have a burette, which is a piece of glassware that allows us to carefully and precisely and accurately measure the volume delivered of a particular solution. So this measures volume delivered. And we're going to put our titrant in this burette because we want to measure carefully and accurately the volume of titrant that we are going to deliver to our sample. And so our sample is going to be contained in a Erlenmeyer flask beneath the burette. Now, what we need is some way to tell us when to stop the reaction. So remember that we need to stop this reaction when the amount of titrant is exactly the amount needed to completely use up the analyte in our sample. So our sample contains the analyte that we're trying to analyze for, and we want to just add the right amount of titrant to completely use up the analyte, no more, no less. And so what we're going to do is we're going to add to this flask something called an indicator. And this indicator is going to change color when the reaction has come to completion. And so that's going to be our clue for when to stop the reaction. And if I stop the reaction when I've just used up the amount of analyte, no more, no less, then if I know the chemical reaction between the analyte and the titrant, and I know its stoichiometry, I can back calculate from knowing the concentration of the titrant. So concentration is known, and I measure the volume. I can calculate the number of moles of titrant used, and knowing the chemical reaction, that allows me to calculate the number of moles of analyte in my sample. So now we just need one last piece of vocabulary, and that is that where the indicator changes color. So the point where we've just added the right amount of titrant to just exactly react with the amount of analyte, no more, no less, is called the end point of our titration. And that's going to be where the indicator changes color. And what's happening there is that I have a stoichiometric amount of titrant and analyte in my flask. So I've just exactly added the right amount of titrant to completely react with the analyte. And so sometimes this endpoint is also called the stoichiometric point, or sometimes you will see it called the equivalence point, because I have an equivalent amount of titrant and analyte in my flask at that point. All of these terminologies, in endpoint, stoichiometric point, and equivalence point, for our purposes, are going to mean the same thing. There are some subtle differences that you may learn about later if you continue on in chemistry, but for our purposes, these all mean the same thing. It means that we have the same amount, a stoichiometric amount of titrant and analyte in our flask. Let's put this idea into practice by doing the following problem. A sample of 49.6 milliliters of river water containing sulfate anions is titrated with a 1 millimolar solution of barium chloride, and a volume of 5 milliliters is required to reach the endpoint of the titration. What is the concentration of sulfate in the river? So we're doing a titration, which means that we're reacting the sulfate anions with barium chloride. So if we write a net ionic reaction for that, we're going to have barium 2 plus from the barium chloride, and it's going to react with the sulfate ions in solution to form barium sulfate, which happens to be insoluble, so it's going to precipitate out of solution when that happens. We know that we used 5 milliliters of a 1 millimolar solution of barium chloride, and each barium chloride contains 1 barium, so whatever number of moles I have of barium chloride, that's the same number of moles of barium 2 plus that I have. So if I want to calculate the number of moles of barium chloride, I need to take concentration times volume, so 1 millimolar is 0.001 molar, and 5 milliliters is 0.005 liters. And so I have 5 times 10 to the minus 6 moles of barium 2 plus that was required to react completely, to reach the endpoint, to react completely with the amount of sulfate that was in the solution to begin with. So since this reacts in a 1-to-1 manner, this number of moles of barium is equivalent to the number of moles of sulfate that was in my solution. And so, because it's 1-to-1, I can say that I had 5 times 10 to the minus 6 moles of sulfate in my river water solution that was 0.0496 liters of solution. 49.6 milliliters is 0.0496 liters. And so the concentration of the sulfate is number of moles divided by volume. And if I calculate that out, I get 1.01 times 10 to the minus 4 molar, or 0.101 millimolar sulfate. So I can figure out the concentration of sulfate in the river water by doing this type of titration.